Hi everyone, Professor Bob Young back at you here. In this instructional video, we're going to discuss vectors. And the definition of a vector is a line segment that has two things. One, magnitude or length, and two, a direction. All right, so I'm going to go ahead and look at this vector to the right here, and we're going to discuss some initial parts of the vector here. So the part here, which is going to be the ordered pair 2, 4, is called the initial point of the vector. And the end here, where the tip of the arrow ends, and this is just pointing the direction, is called the terminal point of the vector. All right, so we'll call the initial point x1, y1 here. And I think everyone can see this is the ordered pair. I'm just going to go ahead and put in 2, 4. And the terminal point is 5, 8, which I'll call x2, y2. And that's how you always want to label these. The initial point is where you begin, x1, y1. The terminal point is where you end, x2, y2. Okay. Now, one thing I have to make a point on here is that unlike geometry, some of you remember your old high school geometry, this looks like a ray if you go back to high school and so forth, and a ray keeps going endlessly forever in that direction. A vector does not. It has a specified length or magnitude here. All right, so we can represent this vector, and a lot of times they'll call vectors different things. Like if they want to label the points here, they could call this point P and this point Q. So there's different ways to label a vector here. So I'll come over here and put PQ, and sometimes they'll put a little vector thing on top of it like that. Or sometimes books will just call it a bold letter, in this case V. And to get this vector, notice we're going to take the x values and subtract them here, x2 minus x1. So I'm just going to go ahead and do that. So that's going to be 5 minus 2i plus y2 minus y1 would be 8 minus 4j. So this vector PQ or vector V, depending on how you wanted to say it, would be 3i plus 4j. Okay. Another way to write this we'll look at in the next slide, but right now we'll go ahead and look at it in terms of I and j. Now I will get to as well is called a unit vector along the x-axis. So every one unit this way, if you wanted to put a mini vector here, would be vector I, and a little mini vector here, unit vector, would be j along the y-axis. All right, so I like to call this 3 along x and this 4 along y. X and y really is what I like to call it. Now the length of this vector, we're going to use this formula. You may remember this from your old pre-calculus or high school geometry or college algebra or whatever. This is the distance formula, and the magnitude or length of the vector is designated by, it looks almost like double absolute value symbols, so we'll call this the length or magnitude of V, and we will just use that formula here. X2 minus x1 quantity squared plus y2 minus y1 quantity squared. Now we've already got that up here, so we'll say that's 3 square plus 4 square. So the magnitude of this vector would be the square root of 25, or it has a length 5. All right, continuing, you will see vectors described in other methods in other textbooks. Now, one is called the component form of a vector. Now, this is from the origin, and they call some of these vectors, well, actually, these vectors standard position to some point x, y there in component form. And they'll write this vector 3i plus 4j in this manner. They'll go ahead, here's another way to write the same vector you will see in other textbooks, pre-calculus books, college algebra books, and so forth. Now, our book uses the I-J combination where it says I is that unit vector along the positive x-axis and J is along the positive y-axis. I discussed that already. And we said the length or magnitude of that vector from the origin to any point xy is given by, this is the distance formula again, because in this case, if you said x2 minus x1 plus y2 minus y1 and you started from the origin, you would just be left with this, the square root of x squared plus y squared. Right? So we found two different ways to write this same vector. The vector could be written in component form, 3, 4, the x and y components, or 3i plus 4j, but there is yet a third way to write this vector, and we are going to call it the trigonometric form or polar form of the vector, which is the magnitude times the cosine of I plus the sine of j. All right, so we're going to also write it this way. So also we're going to look at the direction angle, which is the tangent of this. So if we were going to go ahead here and make a little right triangle out of this, we could certainly do so. And also we're going to find vectors. We can move this vector all over the place as well. All right, so I'm going to go ahead and put 3 here and 4 here. So we've really got a little 3, 4, 5 right triangle here. And this is angle theta, of course. So if we wanted to write this in this trigonometric form, we would say the magnitude of that vector or length is 5 times the cosine of theta here. Now, we'd have to get this angle, so we could use many things to get it, but we'll go ahead and use the tangent of theta equals 4 over 3, y over x, opposite over adjacent. We've seen that many different ways. So we'll say the angle, to get that angle, we're going to take the inverse tangent of 4/3, and we'll go ahead and approximate that on our calculators here. So go ahead, let's go in degree mode. All right, so I got about 53.13 degrees, so I'm going to say the trigonometric form of this vector is 5 times the cosine of 53.13 degrees I plus the sine of 53.13 degrees J. So now we have 3 different ways to write the same vector, and we will be using all 3 of these methods to describe vectors in this section. Now, did you want to check this on your calculator? Once again, if you distributed the 5 times the cosine of 53.13, you would get a number very close to 3. Now, remember, we approximated that, so it could be like 2.99999 or 3.00001. And if we took the 5 and multiplied it by the sine of 53.13, we would get a number close to 4. Right, continuing in this slide, I went ahead and I took our 3i plus 4j, which I had higher, and I just took that vector and I slid it to where the initial point was at the origin. So you can still see that if I go along the x-axis, the x component would be 3, the y component would be 4, this hypotenuse side would be 5, our angle would be the same. So I wanted to next describe equivalent or equal vectors. Now notice these have the same length or magnitude and direction. So if I wanted to look at these 3 vectors, and all I did, I can drag these anywhere. I'll call this vector W. All right, I just took the initial point and I drug it over here, but notice if I go over 1, 2, 3, up 4, it is going to be this same vector. I slid it down here in the 4th quadrant, 3, 4, and again, these vectors you can just take and maneuver them where the initial point and the terminal point are the same x and y components, which gives it the same direction as well. Okay. Now, the next thing we want to look at is what's called scalar multiplication with a vector in terms of I and j. So it says if some vector v, again, that's the bold way to write the vector, equals xi plus yj, and k is a real number, then the scalar multiplication of the vector v and the scalar k is k times v. Or you could go ahead and multiply the x components by k, the y components by k, and that will give you what's called scalar multiples. All right, so a scalar is just a number here. So I went ahead over here and I labeled the vector v, and notice I'm using colors again. I always like to use colors here, and I'm calling v I plus 3j. So you also have to get used to writing vectors and drawing them and seeing how they work. So I just went over 1 on x up 3 on y, and it ends right here, okay? And I said, well, look at what 2v would be. So in other words, if I let the k number, the scalar, be 2, I just doubled this vector here. So I multiplied I plus 3j times 2, and I got 2i plus 6j. All right, so I think y'all can see from the origin here that if this is vector v, this would be the scalar, just doubles it in size, 2v. Now, Young, what happens if you have a negative number for a scalar? So I multiplied v by a negative, which changed all the signs. And notice what happens. It takes that vector and reverses it 180 degrees. So vector v in blue here becomes red. So we would call this negative v, which would be negative I minus 3j. All right, so the scalar number in front can definitely increase the length of the vector, make it smaller. You could hit it with a fraction even, reverse it, and so forth. All right, the next topic here is addition and subtraction of vectors in terms of I and j again. So I said let some vector v equal x1i plus y1j and some vector w be x2i plus y2j. Then the sum of those vectors, which we're going to learn is called the resultant vector here down the line. You just take the x components, add them up, y components, add them up, ij. Or if you're subtracting the vectors, you just subtract the x components and subtract the y components. It's almost like in algebra, you're doing operations on polynomials in a way. You might think of it that way. So if we wanted to add these two vectors, so let's take some examples here. So given vector v is 5i plus 7j and w is 6i minus 9j, it wants us to do some operations on vectors here. So I'm just going to go ahead and we'll work through some of these. So this would be v would be 5i plus 7j, and we're going to add w, which would be 6i minus 9j. Now I know a lot of students go, why did you even bother putting those parentheses on there, Young? You really don't need them when you're adding because you're just going to collect like terms here, and that would give us 11i minus 2j. And it's that easy just to add vectors. All right, now I'll show you why I put parentheses on them in this second example. Let's say if they say v minus w. All right, so we'll just take the same vectors here, 5i plus 7j, and we'll subtract the 6i minus 9j. Now, a lot of students will miss this. Some of you go, I know how they're going to miss it already, Young. They won't distribute that negative sign through there to get minus 6i. And oh, the most missed sign in algebra, ladies and gentlemen. Right there. Be careful. So collecting like terms, you'll get a negative 1i or negative I plus 16j. So a lot of you might already be going, Young, put a lot of these on the test, TQ it. My students say TQ for test questions, all right? So then they can even do some stuff with scalars in here and do some operations on vectors. Now don't panic, don't go, Mama, I can't do it. No, you can take and say 2 times v is 2 times 5i plus 7j, the vector, minus 3 times 6i minus 9j. And we've been down this road many times before. You'll get 10i plus 14j, watch your signs, distributing, minus 18i plus 27j, oh, that most missed sign in algebra again, will give you a total of negative 8i plus, I'm saying, 41j. Now I'm hurting myself, 27 and 14. Okay. And the last example, if you want to, you can pause and do this one. See if you can do it. Come back. That's why I like to do these. You can pause, go through, work them, and then stop the video. Unlike me in class, you can stop, pause, rewind, and fast forward me anytime here. So we'll take a negative 4 times v is 5i plus 7j. So you'll get some of these problems in the homework. And then, oh, Young, you threw a fraction on us, you dog. Oh, no. But I made it a nice fraction that'll nicely go into these numbers as well. I didn't have to. Of course, you could have fractional answers. You could have decimal answers and vectors with those in them. It's not going to be a problem. So this would give us negative 20i minus 28j plus 2i minus 3j. And this final answer should come out negative 18i minus 31j. So you will have some addition and subtraction in terms of I and j and operations on vectors. All right, now where do you use this in real life, Young? Well, this is called the resultant vector here. A geometric method for adding two vectors is shown below here. So what I want to do to illustrate this is I'm going to take this vector u, which it looks like here would be, let's say it's 5i plus 2j. And vector v here in purple, now I'm starting at this initial point here. I'm going to go over 1 on x and up 3 on y. So I'm going to say it is I plus 3j. So not only are we going to add these together to get u and v, now u and v obviously if we added these together from the previous slide would be 6i plus 5j, and you could amaze your friends at parties if you wanted to do this. Notice if you went over here and you went from the origin over 6 up 5, this is called u plus v, or the resultant vector in physics, and we will get to many applications of this creature later and all the things you can do with it. Okay, now also some books would call this the parallelogram effect as well. So I could also, notice I went from the initial point of u to the terminal point and then the initial point of v to the terminal point, which gives me this resultant vector here. But I could also have taken v and started here at the origin. I could go over 1, 3. I don't have this as pretty as the other one. And then I could have taken u and slid it over there. So a lot of places will call this, a lot of instructors' books will call this the parallelogram effect as well whenever you do these. All right, you just kind of see a parallelogram in there. And we learned in earlier sections all the different things you could do with parallelograms. So we'll revisit this resultant vector down the line. Okay, I wanted to throw a slide in here with lots of properties and so forth of vectors. Now the 0 vector is the vector whose magnitude is 0. And it looks like this. And notice the bold 0 means it's a 0 vector. And if you wrote it in terms of I and j, it would be 0i plus 0j. Now I know some of you are thinking, well, how can you have a vector? Isn't that just a point, Young? I mean, with no direction. I mean, I don't really like that either, the zero vector. It's just, I mean, it is what it is. And then we've got some properties of vector addition and scalar multiplication that we will use and see. And if you wanted to just take two vectors and make them up, you could let u be a vector, v be a vector, w be a vector, and you could play with these properties and show they hold. And notice a lot of these properties are from algebra in the past, like vectors are commutative, u plus v equals v plus u. They are associative. If you group the first two vectors, add them together, plus w, it's the last two plus u. Additive identity, anything plus 0 is going to be itself. Additive inverse, any vector plus its opposite 0. And there are also ones for scalar multiplication properties. And again, you can look at any of these and use them if you want to. We could put some examples in here if you needed to. Might hit a few in the homework, but I'll let you go ahead and digest those. All right, the next topic in our studies of vectors is what is called a unit vector. All right, and it says for any non-zero vector v, the vector v divided by the magnitude of v is the unit vector that has the same direction as v. And to find this, you just have to take the vector and divide it by its magnitude. All right, so I put a couple of examples here. It says find the unit vector in the same direction as 6i minus 8j. So I went ahead and I drew this vector in the fourth quadrant. So I went over 6 units on x, down 8 on y here. So what we're going to do first is find the magnitude or length of this vector. Now remember, the formula for that earlier on was to take the square root of the x component squared plus the y component squared, and you're always going to get a positive number when you do this, regardless of the signs on these two. So this will be the square root of 36 plus 64 is the square root of 100, so the length of this vector would be 10. Okay. Now, I also like to use that Austin Powers movie, Dr. Evil, and do with the finger. The unit vector, I say, is like Mini-Me, which I hate to say it, but he passed a while back, so I'm sad Mini-Me passed. But anyway, he was such a good character because he was like the little Dr. Evil. So I always think of the unit vector. I don't know why I think of Mini-Me. I think of crazy things when I teach here. But anywho, I'm going to take this vector 6i minus 8j and simply divide it by its magnitude, which we said is 10. Now you want to write this as a vector too, so you don't want to leave it all bundled up like this. So this would equal 6i over 10 minus 8j over 10. So we could write this vector as 3/5 I minus 4/5 j. And on a unit vector, if you take the square of the x component and add the square of the y component, it will always equal 1, being unit is 1 long. So if we went to graph this, if we went over 3/5 and down negative 4/5, you could see that unit vector, Mini-Me, would be right here. So that would be the vector 1 long in that same direction. All right, so I wanted to show the graph on one of these. So let's do one more of those just to make sure that y'all understand it. So on the second example here, it says find the unit vector in the same direction as 2i minus 5j. So again, we need to get the magnitude of this vector, which we will say is the square root of 2 square plus negative 5 square. You'll be doing a lot of these in the homework early on, getting the magnitude of vectors, the lengths, and possibly even the direction angles and stuff. We could do that as well. And we will say that's equal to the square root of 4 plus 25 is the square root of 29. Now, not always do these bottom numbers come out nicely, as most of you know. So when you go to write this, you'll put 2i minus 5j. You don't want to leave it like this again. You want to write the answer in terms of a vector. So this would be 2 over the square root of 29i minus 5 over the square root of 29j. Then, of course, you know they always like to rationalize the denominators there. So they'll probably write the answer as 2 times the square root of 29 over 29i minus 5 times the square root of 29 over 29j. So definitely, usually this is a test favorite question here, is to find the unit vector. So make sure that you practice enough of these, and I think you'll be okay. All right, so we're going to look at vectors and how they're used in real life in physics and other classes. So what I've got here, this is a crowd favorite when it comes to vectors. You've got a box on a ramp being pulled up the ramp. And here's some things we're going to look at here. Notice we've got 18 degrees here. Inside this right triangle, we've got an 18-degree angle. And let's just see if this makes sense to everyone. The ray BA that's holding the box on the ramp is said to have force of gravity. The magnitude of that vector is the weight of the box, all right? So that kind of makes sense. The magnitude AC here is the force needed to pull the box up the ramp. So notice this vector here, if we were to take and slide it, we could also say, well, that would be AC kind of going this direction as well. So that's the beauty of vectors here. All right, the magnitude BC here, okay, is the magnitude of the force of the box against the ramp. So they will give you some questions in the homework. They might give you a similar drawing, and it says if a force of 10 pounds is needed to pull the box up the ramp, find the weight of the box. All right, now where are we going to put the 10 pounds here? That's what you have to look at. So come down here, look at all this information and see where you would put the 10. And I'll give you a second. I'm going to pause and you pause and come back. All right, so I hope you put the 10 on vector AC here. Notice it says the force of 10 pounds here, and that is the force needed to pull the box up the ramp. And then it says find the weight of the box. We're going to put W here for the weight of the box is the magnitude of BA here. So look at what we have here. We have an old right triangle trigonometry problem here. So are we going to say sine, cosine, or tangent of 18 degrees? All right, people are thinking, are they thinking sine? Are they thinking cosine? Are they thinking tangent? It is going to be, I believe, the sine of 18 degrees equals 10 opposite over W hypotenuse. Now, Young, why did you go sine? Why did you go sine? Be careful. You have to make sure you remember your right triangle trig. So solving, we're going to multiply both sides by W. We'll say sine 18 degrees times W equals 10. Divide both sides by the sine of 18 degrees. So you will find a lot of vector problems in other classes besides this one here. But I think that one makes a lot of sense from what we've done in the past. And let me go ahead and get that answer. All right, I came back with about 32.36 pounds as the weight of the box. All right, so let's look at some more application problems. We've looked at a similar problem earlier, but let's look at it one more time here. It says writing a vector in terms of its magnitude and direction. Now it says let vector v here be a non-zero vector. If theta is the direction angle measured from the positive x-axis to v, then the vector can be expressed in terms of its magnitude and direction as follows. So this is like the trigonometric way we've looked to write vectors here. All right. Now what it says here, it says the wind is blowing at 20 miles per hour in the direction north 30 degrees west. Express its velocity as a vector v in terms of I and j. All right. Now in physics, if they give you the 20 miles an hour, they're coming right out. It's kind of like they're giving you the magnitude right there. So this is kind of nice. They'll just come right out and hand you that. Now, if you go to write this angle, if you put 30 degrees in here, you're in trouble. All right, so notice I went up here and we haven't done the old bearing problems in a while. I put north 30 degrees west going this way. So you always go north first and then east or west if you remember that. So this is good exam review right here. But the angle we need is this angle for theta, so be careful. And that would be 90 plus 30 or 120. So if we're going to write this vector, we're going to say the magnitude is 20. So we've got 20 here times the cosine, let me go ahead and put that, of 120 degrees I plus the sine of 120 degrees J. And I think I should have some parentheses around these guys right here. Oopsie. So make sure you add that. Sorry about that. Now we're not done yet because they don't want it in terms of they don't want the trigonometric form. I think they want us to keep going here. So the cosine of 120 degrees we know is negative 1/2 I. There's that darn unit circle again. Plus the sine of 120 degrees is the square root of 3 over 2j. So distributing through here, we're going to get the final answer of negative 10I plus 10 times the square root of 3j. This would be our vector with this described. All right, this last example could be the killer. It says the magnitude and direction of two forces acting on an object are 90 pounds at south 72 degrees east. So here's what I did here. I'm going to put my 72 degree angle here. I'm calling this first vector F1. So this is going to be 90 pounds is the force on it, which we're going to learn is its magnitude in physics. All right. And there's a second vector, it says it's 60 pounds at north 65 degrees east here. So again, you have the old bearing problems are coming back. So make sure that you know that this is the second vector. And I tried to kind of make this, if this is 90, I tried to make this force here or length or magnitude 60 pounds here. I might not be perfect, but it's close enough for government work. Now it says find the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree of the resultant force. All right, so what we need to figure out here is how to get F1 plus F2 first. All right, so here's what we're going to do. We're going to write this in the trigonometric mode here. We're going to say that the first vector is going to equal 90 times the cosine of what angle here. Now here's where you have to be careful. If this is 72 degrees and we need this angle, I think we're going to have to either get the positive or negative angle. Now you guys know me, I always like to get the positive angle here. So how would I get this angle? Well, it would be 90, 180, 270 plus 72 would be 342 degrees. So I'm going to say 342 degrees I plus the sine of 342 degrees J. Okay, so I'm going to call that the first vector F1. Now the second vector, again, be careful. F2 here. Notice that they gave us this bearing north 65 degrees east, but that's not the angle we need either. We need this angle in here to write this F2 vector. All right, so it's going to be 90 minus 65. So really the angle you need when you're writing these vectors, it comes back to all of your trigonometry we have learned as we have progressed this semester. So y'all should start feeling the power right now. All right, so F2 we're going to say is 60 times the cosine of 25 degrees I plus the sine of 25 degrees J. Now let's continue. So to get F1 plus F2, I'm going to go ahead and I can distribute this 90 through. Now I'm going to put the X's with the X's and the Y's with the Y's here and see if this makes sense to everyone. I'm going to put 90 times the cosine of 342 degrees plus 60 times the cosine of 25 degrees. So I'm adding the X components here, and I'm going to do this on my calculator all in one swoop to make it easier. I plus 90 times the sine of 342 degrees plus 60 times the sine of 25 degrees, J, if that's all right with everybody. And I've already worked this out, so you guys can pause here and try it on your calculator. Make sure you get the same numbers as I did. But the F1 plus F2, the sum of those two force vectors in physics would be 139.97 I. So again, I'm kind of looking up here, going to the nearest hundredth on these. And then you have to be careful rounding always when you're doing problems like this, plus 2.45 J. So putting this in, 139.97 in that parentheses, putting this in minus 2.45 J. Now, in order to get the resultant force here and the direction angle to the resultant force, we are going to have to find now the magnitude of these creatures, the resultant force here. So I didn't promise you a rose garden, ladies and gentlemen. It is the square root, make a giant square root here, of 139.97 square plus negative 2.45 square. And I came out with that answer is equal to 139.99 pounds. I'll just round that. I know it says up there what to round it to, but I'm going to just call it 140 pounds. All right. So the combination F1 and F2 force, so if this one's pulling 90, this one's pulling 60, all right, the resultant force, the resultant magnitude would be 140. Now, what direction is this angle right here? Now, that's a pretty thin angle, isn't it? And I tried to draw this out as best I could. Now, of course, these aren't exactly 65 and 25 degrees, and this isn't exactly 72, but I got it as close as I could. I mean, so here's what we're going to do next. We're going to find the angle by taking the tangent of theta, saying that's y over x, which, yes, it's still these numbers here. It's going to be negative 2.45 over 139.97. So continuing, to get the angle now, we have to undo tangent by taking the inverse tangent, the arc tangent of both sides, or what Young likes to call the angle getter. So it would be the inverse tangent of negative 2.45 over 139.97. Sorry, that decimal doesn't look real good over here. Let me fix that. All right, so what I ended up with is approximately negative 1 degree in there. So it almost looks like it could be that resultant direction 1 degree. But of course, if you wanted to get the angle as a positive, you would add 360 to it, and you could say, or 359 degrees. Now, these angles, of course, are coterminal. More good exam review. So this is Vectors. Bob Young signing off. Bye. All right, I wanted to take a few examples from the homework here, and it says here a vector is described. Express the vector in terms of I and j. So it says a quarterback releases a football with a speed of 46 feet per second at an angle of 60 degrees with the horizontal. So he's throwing the ball down the field. We need this vector, ladies and gentlemen. How do we do it? Stop. All right, so yes, we are going to use this formula, the magnitude of V, which we're going to say the speed in physics now is 46 feet per second, so we're just plugging that in there, times the cosine of the angle, which is 60 degrees, I, plus the sine of 60 degrees J. All right, now once again, back to the unit circle when you can do it. The cosine of 60 degrees is going to be 1/2 I, the sine of 60, square root of 3 over 2j, multiplying the magnitude through 46 or force, we're going to get 23I plus 23 times the square root of 3j. So he's throwing it. It's touchdown, the Raiders. All right, so we'll plug that in and check it. Bang. All right, for our last application problem, this one says two tugboats are pulling on a large ship that has gone aground. One tug pulls with a force of 2,500 pounds in a compass direction of 56 degrees. Now, if they don't say north something degrees east or south something degrees west, whenever you see one like this, and I think this is good exam review, we did these earlier in the semester, that you are going from true north. See, so this would be 56 degrees in here. And this one's pulling at 2,500 pounds, so we'll call this one F1, 2,500 pounds of force this tugboat's exerting here. So we've got to save this tugboat that's run up off the ground here. Or, you know what I always say, when people in math make mistakes, people die. Yeah. All right. And the second tugboat we're going to call F2 here has a force of 1,800 pounds, so he doesn't have quite as much oomph in the pull as the first tugboat. And the compass direction here is 101 degrees, so I went 90 and then another 11 degrees right in here. So I hope you all agree 90 and 11 will get 101. That's a bad 11 in there, sorry. All right, so this is similar to the example we did previously. Now, if you want to try to go ahead and get the force vectors here, F1 plus F2, this would be a good time to pause and to practice. So you can do that, but I'm going to keep going here. So if you're not pausing, you're just following along. So we're going to say this first tugboat is going to be in trigonometric form. The magnitude or force 2,500 pounds times the cosine of what angle here, ladies and gentlemen? Do not put 56 degrees. You're going to put what? 34 degrees. Oh, you have to be careful here. 34 degrees I plus the sine of 34 degrees J. Okay, so that would be the first one. F2 is going to be 1,800 times the cosine of, I'm going to put negative 11 degrees I, just to show you in physics, you don't always have to have the positive angle and come around here on these especially. So Young, I've never seen you do that before. I'm doing it. Sine of minus 11 degrees J. So very similarly here, if we want to find, it says, now on this one it says round the final answer to the nearest tenth, and all intermediate values to the nearest hundredth. All right, so I'm going to pause and come back to save some video time here. All right, so I went ahead and I added the two vectors here, F1 plus F2, and I've got 2,500 cosine 34 plus 1,800 cosine negative 11 degrees. I ended up with 3839.52I. Did the same thing in here with the sine, 2,500 sine 34 plus 1,800 sine minus 11 got 1054.53 J. So now what we're going to do next is figure out thereafter the magnitude of this resultant force here. So we're going to take the magnitude of these. All right, so I'm going to pause and go ahead and do this and come back. All right, so taking the square root of the x component square plus the y component square, I ended up with 3,981.7, which is, it looks like it wants it rounded to the nearest tenth. All right, and make sure your answers make sense as well here when you're doing these. So you've got a tugboat, let's say tug one's pulling at 2,500 pounds this direction at a compass direction of 56 degrees, and tug two's pulling at 1,800 pounds. Now I think your resultant force, if you think about it, if you took this vector and you put it out here, remember the resultant force would be out here somewhere, so you want to always keep things in mind too. And let's see if this makes sense. Now we'll get the direction angle next by taking the tangent of theta and setting that equal to y over x, which we said is 1054.53 divided by 3839.52. And we'll say that theta is going to be the inverse tangent of this. Watch me get lazy. So we will get that as well. Let me come back. I'm going to pause here. All right, so I ended up with the inverse tangent of y over x is about 15.36 degrees, and I could kind of see that out here. So let us put our two answers in and see how we did. All right, so I put the first one in, good, 3981.7, and it says the resultant force is, now it says this one, it wants the final answer rounded to the nearest tenth as well. All right, so instead of 15.36, I think we'll put 15.4 degrees in there. Uh-oh. Let me check that again here. I'm going to have to go back. So sometimes that happens. Don't lose faith. All right, now we did nothing wrong, ladies and gentlemen. Don't panic. You have to be careful when you read these questions sometimes. Notice it says here, round the answer to the nearest tenth as needed, but also it says the compass direction of the resultant force. Now we got the direction, the 15.4 was from the positive x-axis, but remember the compass direction is from true north, so it would be 90 minus 15.4. Oh, I'm glad I did this one, so when y'all are doing that homework, you won't be going crazy. 74.6 is your answer. Bang. All right, Bob Young signing off. Get on those vectors and have fun with them. Bye.